time now to talk about the p-value. And the p-value is a bit of an esoteric statistical concept, but it is central to every medical study. It is talked about all the time, even if people don't use the term p-value, so it is really critical that you know what it is. So the goals of the lecture today are to explain how we decide if the results of a study are significant, and significant is in scare quotes there. Describe the p-value, the primary score that drives medical studies. Explain exactly how so many people misinterpret the p-value and what you should really do to interpret whether a study is significant. Now, to give a visceral understanding of how the p-value works, I'm going to crowdsource this a little bit. So here we go. We have a quarter here. It's a mysterious quarter. It may be an ordinary quarter, or it may be a quarter that has heads on both sides. Okay? I'm not going to tell you which it is. I'm just going to flip it, and you have to decide after each flip whether you think it's a two-headed coin or a regular old-fashioned coin. Okay? So the first flip comes up and it's heads, and the next flip is heads, and the next flip is heads, and the next flip is heads. Are any of you starting to get a little suspicious about this coin? No? All right. Think about it. How about this flip? Heads. 6. Heads. Probably you're feeling a bit more suspicious. Heads. 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 People pretty suspicious about this coin yet? Okay. There's one last heads. Another last heads. 12 heads in a row. People are getting pretty darn suspicious at this point. Okay, so how weird was that? How weird was it that we just got 12 heads in a row? Well, this is a simple matter of probability, a simple matter of statistics. You can say that if we flip it once, our chance of getting heads, assuming the coin is just a normal run-of-the-mill coin, you know, a single flip, 50% chance of getting heads. So that's 50% probability there. 2 heads in a row, assuming you have a normal quarter, 25% chance, 0.25, okay? 3 in a row, 12.5%, and so on down the line. If I have a normal quarter, it's pretty unusual to get 10 heads in a row. Around about 1 in 1,000 times, you might get 10 heads in a row like that. All right, so you felt that. That was intuitive to you. And somewhere between 4 and 5 head flips in a row, you started to get suspicious, right? You started to think, maybe there's something weird about this quarter. Maybe it's not an ordinary quarter after all. And you'll note that the probability between 4 and 5 head flips is between 0.03 and 0.06, somewhere around the vicinity of 5%. And there's something just viscerally strange when things start happening around that probability of 5%. And in fact, that's why we define statistical significance at that probability level. So statistical significance is arbitrarily defined as a p-value of less than 0.05. Now, a p-value is just the probability of seeing results as strange as the results you saw, or stranger, assuming that there's nothing special going on, assuming it's just a run-of-the-mill, ordinary quarter, nothing strange going on here, okay? So we set the definition of statistical significance at 5%. So it's a little weird, 4 heads in a row, but not crazy, and keep that in mind, okay? So when a study reports a p-value of 0.04, just think, that's about 4 or 5 head flips in a row, assuming there's nothing here, assuming the coin is a regular coin, or assuming the drug doesn't work. Now, statistical significance has nothing to do with clinical significance, okay? Clinical significance tells you, oh, well, this is an important medication that will save lives and that people should take. Statistical significance, like I showed you there, is purely a mathematical construction. To give you a sense of that, think about testing 2 cars, okay, to see what their top speed is. Now, we might show statistically that one car has a top speed of 161 miles an hour and one car has a top speed of 160 miles an hour, and we can show that those are statistically different, that they are not the same top speed, they are different top speeds. But honestly, between 160 and 161, do you care that much? Maybe a few of you do. I certainly don't. I don't think I've ever gone 160 miles an hour in a car. I don't want to ever go 160 miles an hour in a car. So this is a difference between statistical significance and clinical significance. All the time in the news, you'll see them say, oh, this finding was statistically significant, and it sounds like it's a medical breakthrough. It's not. Clinical significance, which is a subjective determination, is what really matters. Now, how weird are your results? That is what the p-value is telling you. It says, assuming there's nothing cool going on, okay? Assuming the drug doesn't work, assuming the intervention is completely ineffective, assuming the coin is a regular coin, how weird are the results that you saw? Well, if I flip a coin 10 times and get 6 heads, you remember this from the prior lecture, that's not that weird, right? That's not crazy. You wouldn't feel that that's very weird. But if I flipped it 100 times and got 60 heads, that feels a little weirder. And if I flip it 1,000 times and get 600 heads, that's even weirder still, right? So there's something that is linked to sample size here. So in case you didn't do the math in your head, I got 60% heads in each of these experiments, right? But the experiment that had 1,000 coin flips was much weirder. The results were much weirder, despite still getting 60%. They should feel weirder to you. And the p-value actually accounts for that, right? So the p-value for getting 6 heads, how weird this is 0.75. All right, so that's not statistically significant. It says, you know, assuming this is a regular coin, getting 6 heads in a row is not that crazy. 0.75, it could happen all the time. 100 times in a row and getting 60 heads, well, that p-value is 0.06. That says, assuming it's a normal coin, you know, getting 60 heads out of 100, well, that's a little weird, right? We're getting to that threshold of 0.05 where we start to say, this is a bit strange, assuming it's a normal coin. And if you do it 1,000 times and get 600 heads, you get this incredibly low p-value. If you did that, you would start to say to yourself, okay, wait a second. Maybe this isn't a normal coin, right? Like this is this would be a really lucky set of flips if I got 600 heads out of 1,000 flips. So the p-value is the chance of seeing results as weird as the results you saw, or weirder, assuming it's a normal coin. I say this again and again and again. It's under the assumption that nothing interesting is going on. So the p-value accounts for the number of flips, right? It accounts for the sample size. It builds it in. It's cooked into the p-value, which is great. And we need to be aware that there's a technical term for nothing interesting going on. Nothing interesting going on is called the null hypothesis. So we often think of medical studies in the context of 2 hypotheses. The null hypothesis, the drug doesn't really work. And the alternative hypothesis, the drug does work, okay? So the p-value is calculated assuming the null hypothesis is true. It assumes the coin has heads and tails just like every other coin and just quantifies how weird your results are. So the hypothesis testing framework is just this. The null hypothesis, it's a normal coin. The alternative hypothesis, it's a weighted coin or a coin that's kind of special, different in some way so that it comes up heads more often. All right. This brings us to the question, which is sort of, I like to think of as how different is different. So whenever I measure 2 things, or I measure a value in 2 different groups, I'm never going to get the exact same number, right? It's just not going to happen. So I have to quantify somehow how different are these groups? How sure am I that these groups are different from each other really? Remembering that sampling framework, it's like how sure am I that this bag has more gold coins than this bag if I can only sample a few from each bag? All right, so just to give you an example, I measured the weights of 100 male internal medicine doctors like me and 100 male surgeons. The null hypothesis, okay, is nothing as interesting is going on. What's the null hypothesis here? The null hypothesis here is the average weight is going to be the same. All right, so the average weight among the medicine guys was 175 pounds. The average weight among the surgeons was 180 pounds. So these are different. Are we done? Do we say to ourselves, okay, well, surgeons are on average heavier than medicine guys? Well, not really, right? Because I just took a sample of medicine guys and surgical guys. I didn't measure every single one in the world, and I'm more interested in kind of generally who's heavier. Okay, so what we have to ask ourselves is, assuming the null hypothesis is true, assuming the average weight is the same, doesn't vary by your surgical or medical specialty, how weird is it that I would get these particular results. How weird is it that I would get 175 as an average for the medical guys and 180 as an average for the surgical guys? Well, that's a p-value, right? One of the groups is going to be heavier. I'm never going to get exactly the same average for both groups. I know that. But remember, the issue of sampling. I'm not measuring every surgeon in the world. I'm taking, hopefully, a random sample. So if the surgeons turn out to be heavier, how sure am I that they would be heavier if I were able to measure every single surgeon in the world? In other words, how weird are my results, assuming there are no major differences in weight by medical specialty? Now, there are equations for this, and this happens to be one of the equations you could plug in to calculate a p-value using your data. We are not going to go through this math. This is very intimidating looking math. It's not as hard as it looks, but it's intimidating looking. How you calculate p-values is a lecture in itself. You just need to know how to interpret them, and remember, the lower it is, the weirder your results are. And 0.05 is an arbitrary threshold defining statistical significance in medical studies. But be careful. So here's a warning. Let's say I flip my coin 5 times and I get 5 heads in a row. Assuming this is a normal coin, right? This is just a coin that you know, head and a tails. This is pretty unusual. The p-value is 0.03. That's a bit unusual to get 5 heads in a row. Not crazy. It would happen 3% of the time. It's a little interesting. So you could say that given that the coin is normal, it's a regular old coin, I'd see results this weird only 3% of the time. That's a fair statement. This is not the same as saying, I am 97% sure this coin has 2 heads. Okay? The results you found were a bit weird, assuming the coin is normal. It does not mean that the coin is abnormal, and people get this wrong all the time. They say, oh, well, the p-value is 0.03. That means there's only a 3% chance this is a regular coin. No. The p-value already assumes it's a regular coin. The p-value doesn't say anything about whether it's a regular coin or not. It assumes it's a regular coin and is just telling you how weird are your results, assuming it's a regular coin. So let me give you an example of this. If we have situation 1, your friend is walking down the street, sees a quarter on the ground, picks it up, and flips it, and gets those 5 heads in a row. P-value, 0.03. Situation 2, a shady street magician comes up to you and picks a quarter out of his pocket, and he makes a bet with you that if he gets heads, you pay him $1, but if he gets tails, he'll pay you $2, right? It would be a great bet if it was a normal coin, and he proceeds to flip 5 heads in a row. You still have a p-value of 0.03 in both of these situations. Which situation do you think is more likely to have the coin with 2 heads, right? It's the shady street magician. You're with me on this. You got to be with me on this. Don't trust the shady street magician with that quarter. So you took information from before you saw the coin flips to use what the coin flips told you to make your final conclusion. You essentially were suspicious before that street magician even flipped once. And when his flips confirmed your suspicions, you became even more suspicious. Whereas your friend who picked it up off the street, you weren't suspicious it was a 2-headed quarter. That's a really weird thing. Why would there be a 2-headed quarter lying on the side of the street? You're not suspicious at all. So you have to interpret p-values in the context of your prior suspicion that something is going on, that the alternative hypothesis is true. That prior suspicion has a formal name. It's called the prior probability, and we'll talk about that more in future lectures. But just to know, the p-value doesn't tell you whether the drug works. The p-value just says, how weird is this data, assuming the drug doesn't work at all. Now, you'll see this in the headlines all the time, okay? So here are 2 p-values that are the same, 2 different headlines. 1, seatbelts save lives, p-value equals 0.04, a statistically significant result. Would you believe this study that seatbelts save lives, right? So what's the null hypothesis here? Seatbelts don't do any good. The alternative hypothesis, seatbelts save lives. So they're telling us that the p-value is 0.04. Whatever data they had, assuming seatbelts don't work, the data that they showed was pretty weird in a world where seatbelts don't work. So we would say, yeah, that makes sense. Seatbelts probably work, because we kind of believed before the study was even done that seatbelts worked. It makes sense that they work and they should work and that kind of thing. Now, if you had a study that said astrological sign predicts income with the same p-value, they're telling you, assuming the study is truthfully reported, they're telling you that Under the null hypothesis, the astrological sign doesn't matter at all, this data is a little weird. You'd only get data this weird 4% of the time. That's pretty weird. Does that mean that you're now 96% sure that astrological sign predicts income? No. Chances are you just got lucky or unlucky, however you want to think about it. This was just one of those studies. 4% of the time you were going to get results this weird. It happened to be one of those pulls of the jackpot lever where you get 4%, where the 4% comes up. Okay, so you have to interpret these results in the context of your prior belief in whether this thing is going to work or not. So p-values do not tell you the chance that something is happening. To figure out the chance that something is happening, like if a drug or intervention works, you have to know how likely the drug was to work before the study happened, before the coin got flipped, your prior suspicion that something strange was going to be going on. How do you quantify that? Well, you can read other studies that have been done. You can use biologic plausibility, like seatbelts really should work because, you know, they restrain you in your seat, and that seems to make sense, whereas astrological signs really have no biologic plausibility behind them. You can use any metric you want, but you do have to come up with a sense beforehand of how likely you think something is. Remember, extraordinary claims require extraordinary evidence. That is why that maxim is true. Because something being a little bit weird, if the claim is very extraordinary, chances are you just got a little bit weird data, not that you are blowing up the entire underpinnings of modern science. So how does this work in a real study, just to show you an actual example? So here's an article close to my heart as a kidney doctor, looking at our old friend Lipitor here to prevent acute kidney injury after cardiac surgery. So patients after cardiac surgery, sometimes their kidneys stop working. And this was a trial to see if giving them some atorvastatin, some Lipitor, would improve that. And what you see is that the number of patients who had acute kidney injury in the Lipitor group was 20.8%. compared to 19.5% in the placebo group. So if that's all we looked at, we'd say, oh, well, the atorvastatin group had more acute kidney injury, 20.8 versus 19.5. Does that mean that this drug, you know, hurts the kidney or something? Well, let's look at the p-value, okay? The p-value is calculated at 0.75. What does that say? The p-value says, how weird is this data, 20.8 and 19.5, assuming that Lipitor is inert? It doesn't do anything. It doesn't hurt your kidneys, doesn't help your kidneys. And the answer is, it's not that weird. This data is pretty common. You know, 75% of the time you'll get data this weird or weirder, okay? So this p-value of 0.75 we would call not statistically significant, and we would say not that Lipitor hurts the kidneys, but that Lipitor doesn't seem to have any effect one way or another. So here are our take-home points for today. P-values are a measure of how weird the data is. I'm going to say it again, assuming nothing weird is actually going on. The threshold for statistical significance, p less than 0.05, is arbitrary and has nothing to do with clinical significance. We want p-values to be the chance that the study is wrong, but they are not. Remember, p-values assume that the thing isn't working, that the medication doesn't work. They don't tell us how likely it is that the medication works. You need to know the prior probability of the study to figure that out, and that is somewhat subjective. So interpret a p-value in the context of your prior belief that the thing that is being tested could actually work. Thanks very much.